This is part one of Earth. We start with the key question. Earth. Overview from space. This is the planet you are standing on right now, and most people have never really looked at it. We are starting a full series on Earth, and the first question to answer is the most fundamental one. What kind of planet is this, objectively, when you compare it to everything else in the solar system? That question matters more than it might sound. Most of what we think we know about Earth is filtered through the fact that we live here. Strip that away, and you are left with something genuinely unusual. Not the best planet, not the most dramatic, but one that sits in a very specific set of circumstances that, taken together, are difficult to replicate. Let's look at it properly. Section 1. Position and scale. If you have been following the Solar System Reference Collection here on Orbital Dispatch, you will know the format. Every body gets the same questions, so you can compare them fairly. No favoritism, just because we happen to live here. Earth is the third planet from the Sun. Its average distance is approximately 149,600,000 kilometers, and astronomers use that number as a standard unit. 1 astronomical unit, or 1 AU. When we say Jupiter is 5.2 AU from the Sun, that means 5.2 times the Earth-Sun distance. It is the baseline against which everything else in the solar system is measured. One orbit takes 365.25 days. That quarter day is why we add a leap year every 4 years. A small correction to keep the calendar aligned with actual planetary geometry. Orbital speed averages around 29.8 kilometers per second. At that speed, traveling in a straight line, you could circle the equator in roughly 22 minutes. Worth holding in mind as we go, Earth's orbit is not perfectly circular. It is very slightly elliptical, and that has some interesting consequences for how the planet relates to the Sun, and for why seasons work the way they actually do. We will come back to that. Earth's equatorial radius is approximately 6,371 kilometers, largest of the 4 rocky inner planets, though only just ahead of Venus. It is also the densest planet in the solar system, at around 5.5 grams per cubic centimeter, meaning a lot of what makes up this planet is heavy material, packed tightly together. Section 2. Composition and structure. From orbit, you see a thin skin of gas, water, and rock. What is underneath is a different matter entirely. The crust, the part we live on, is between 5 and 70 kilometers thick, depending on whether you are under ocean or continent. Beneath it is the mantle, silicate rock extending roughly 2,900 kilometers down. Solid, but over geological time it moves. It convects very slowly, like an extraordinarily thick fluid, and that movement drives plate tectonics. Plate tectonics is one of the most important things about Earth as a planet. The surface is broken into large sections, plates, that shift relative to each other over millions of years. Collisions build mountain ranges, separations open rifts where new crust forms at mid-ocean ridges. Subduction zones where one plate dives beneath another produce volcanism and earthquakes. Not every rocky planet works this way. Mars shows no evidence of active plate tectonics today. Venus almost certainly lacks Earth-style plate motion. As far as we know, Earth is the only planet in the solar system with a globally active modern tectonic system, and that matters for reasons we will get to. Below the mantle is the core. The outer core is liquid iron and nickel, extending from around 2,900 to 5,100 kilometers depth. The inner core, from there to the center, is solid iron under extraordinary pressure, despite temperatures that would ordinarily keep it liquid. That liquid outer core is important. As it circulates, it generates Earth's magnetic field, which does something specific that has direct consequences for whether the planet can support complex life. We will close that shortly. Section 3. What makes Earth unusual? Surface gravity is, by definition, 1 g, 9.8 meters per second squared. The baseline. The Moon has about 0.16 g. Mars, around 0.38. Jupiter's cloud tops, roughly 2.5. Surface temperature ranges from around minus 89 degrees Celsius, recorded at Vostok Station in Antarctica on the 21st of July, 1983, to around 56.7 degrees at Furnace Creek in Death Valley. The global average sits near 15 degrees Celsius, kept relatively stable by the atmosphere and ocean system, which gets its own episode next. Time to close both of those open threads. Because Earth's orbit is elliptical, the planet is actually closer to the Sun in January and farther away in July. If you live in the Northern Hemisphere and assume summer happens because we are closer to the Sun, you now know that is not right. It is farther away during Northern Hemisphere summer. Seasons are driven by axial tilt, 23.4 degrees, not by distance. That tilt means summer brings a higher sun, longer days, and more energy absorbed by the ground. Distance is a minor factor by comparison. Earth's magnetic field, generated by the churning liquid iron outer core, forms a magnetosphere that deflects the solar wind, a continuous stream of charged particles from the sun. Without it, the upper atmosphere would be gradually stripped away over geological time. That appears to be exactly what happened to Mars. Mars lost most of its magnetic field billions of years ago, and its atmosphere is now less than 1% as dense as Earth's. Earth's magnetosphere has been protecting the planet's atmospheric envelope for around 4 billion years. It is not dramatic to look at, but it may be one of the fundamental reasons complex life exists here at all. One more feature worth naming: the Moon. Earth has one large natural satellite relative to its own size. The Moon's diameter is about 27% of Earth's, which is an unusually high ratio for a rocky planet. Mercury and Venus have no moons. Mars has 2 small, irregularly shaped captured bodies. Current thinking holds that the Moon formed around 4.5 billion years ago, from debris thrown out when a Mars-sized body struck the early Earth. The giant impact hypothesis. Over long timescales, the Moon's gravity stabilizes Earth's axial tilt, which may have kept the climate more consistent than it would otherwise have been. That is an active area of research, and the models continue to be refined. Subscribe so you do not miss it.